dynamic mechanical loading. Well, thank you.
Assalamu alaikum. I'm very happy to present for you our work titled Investigation of an eco sandwich composite pipe standard dynamic mechanical loading. This work is of our teams. I am Hakim Maizia, Reverend Aidin, and Professor Abdulrazak. So, first of all, the synthetic sandwich pipe, we have many advantages of these kind of materials, like corrosion resistance and lightweight and durability, and we have also a high density and a high energy of these synthetic materials. In other hand, we have many disadvantages of this kind of materials, like no recyclable and high energy consumption, no biodegradation, and no renewable. We have also the problem of higher initial cost and the risk of high dioxide of carbon emission. Due to these disadvantages, we move to propose a new kind of materials like a natural fiber. To use it with this kind of material, we can design a new form of pipeline with many kind of natural fibers. Natural fiber can be used in many domain of engineering, like aeronautic, military, and sport equipment, textile, automotive engineering, and civil engineering, musical instrument, and electronic devices. In our work, we will focus on the use of this natural fiber in the domain of sandwich tube. The objective of this work is to design an eco sandwich pipe for gas transportation and with the analytical approach and numerical model. Analysis of stress and strain was established using the three-dimensional anisotropic elasticity theory. Based on the TRIO criterion for the scheme parts and the Bomis criterion, we can evaluate the reliability of the two parts of this kind of structure. As a first contribution to simulate the fatigue phenomena of eco sandwich pipe, the static model is developed by introducing the dynamic loading of internal pressure, the context of elasticity hypothesis theory, and the charge is inner pressure with loading, cyclic loading. The form is used here is triangular loading. To achieve this goal, we use this flow chart or this algorithm to evaluate the reliability of the pipe studied or the sandwich studied in this work. And for the sequence sequences, we have 5 cases of sequences. In these sequences, we change the angle of liner of the continuous fibers with the number of layers. The material studied in this case, we have 2 bio source of fibers as jute and the pulp, and for the synthetic fiber, we study the case of glass fibers. This 4 figure represent the influence of when we change the material and the sequence of layer for the radial stress in the figure number 1. In the figure number 2, we have the variation of the hoop stress of this pipe. In the third, we present the variation of axial stress, and in the last one, we present the shear stress of this pipe. First of all, this figure represents the variation of radial stress. We can conclude when we change the sequence of layer and the material, the radial rest constant, and the changement of the change of this parameter do not have any impact of the behavior of this pipe. In the second figure, we present the variation of hoop stress with the time, and we can conclude the good behavior of the case of pulp epoxy and the jute epoxy in place of the pulp and the glass fiber. In the third figure, we can show the axial stress variation with time, and we can conclude the good behavior of the jute fiber and the pulp fiber in the phase of the glass epoxy with the sequence number 1, number 5, and number 5 for the pulp epoxy. And the last one, we can show the shear stress variation with the time, and we can conclude the good behavior of the jute fiber with in the case of the sequence number 1 and the sequence number 5. This figure represents the Tsayu criterion variation in the 2 cases. The first one is the glass epoxy with sequence number 1 and the jute epoxy with sequence number 5. And this figure represents the behavior of the core of our pipe. We can show the Momises criterion variation with 5 cases of materials, and with 4 cases of or 5 cases of materials and sequence of layers. After this analysis, we can conclude some conclusion. First of all, the developing dynamic model, which consists of repetitive loading of pure internal pressure. In preliminary, we step in the analysis of fatigue of tubular structure and the loading which should not exceed the tolerated threshold. In the second, we can conclude the analytical solution developed here can be efficiently used to predict the dynamic behavior of the present pipeline with a cyclic loading. And also in this study, the results show what the sink of the axial strain and is significantly influenced by the mean amplitude of the cyclic loading and the reflex of the imposed boundary conditions. The results highlight that hoop and axial stresses are highly dependent on the properties of the materials involved. And the hoop stress and axial stresses demonstrate that the inner skins are certainly strained by compared to the outer layer. This may result in the commencement of the progressive damage to the inner wall of the sandwich cube. The finding of axial strain indicate that the structure is compressed in the axial direction. In this context, the jute epoxy combination exhibit favorable behavior compared to the glass epoxy case. And with a concentration in the core, the radial strain values show a condition of compression of the sandwich pipe wall through its thickness. The pressure examined in this study is three times the anticipated service pressure, which is accepted to be 30 bars. This provides a substantial safety margin when utilizing biocomposites in the production of sandwich tube. And finally, by increasing the number of layers, substituting biofibers for synthetic fibers produces suitable results and can play the same role at this point of analysis. And thank you for your attention.
Any question?
Congratulations for the presentation.
Thank you.
I want to know how you made the pipe composite. How you made? How you?
Yeah, it's only simulation.
Simulation is.
Simulation, not.
Okay.
It's an analytical model.
Okay.
But how? Okay, simulation. But how is in order to make after?
Yes.
Yeah. Do you know how make this pipe, this piece and composite, how put maybe circular more.
Yes, yes, it's possible to make it because we can prepare the third, first of all, the inner part and the second part and the third part or the outer part of this pipe. Yes.
Okay,
Thank you.
Autre question? Quelle est l'origine de l'anisotropie et de l'élasticité? Vous avez parlé de l'anisotropie et de l'élasticité.
Yes.
Quelle est l'origine de cette anisotropie?
L'origine, c'est à l'échelle micro, nous avons la matrice et les fibres. Alors nous avons généralement deux matériaux. La variation de matériaux va engendre l'anisotropie dans les structures à base de composite with fiber and matrice.
Il y a une certaine énergie qui va donner cette grandeur suivant une direction bien déterminée.
Oui.
Donc cette énergie, d'où vient-elle?
Ça vient de l'architecture de la structure elle-même. Et donc, puisque nous avons les fibres immersives dans la matrice. Alors, généralement, dans notre cas, c'est les fibres en joue ou bien l'hiver, et la matrice, c'est l'époxy.
Et certainement, il y a certaines forces qui vont induire cette énergie pour que l'élasticité garde une certaine valeur dans une direction bien déterminée. Quand je dis un matériau, il est anisotrope. C'est-à-dire qu'il présente une certaine propriété dans une direction bien déterminée.
Oui, chaque direction a
Quelle direction une structure avant? Là.
chaque direction. La direction, c'est la direction du fil. La direction du fil.
De croissance.
On peut jouer sur l'angle d'orientation du fil pour réaliser la configuration choisie. Et généralement, d'après les normes utilisées, les pailles multicouches à fibre blanc, généralement, nous avons l'angle d'environ plus ou moins 55. C'est la configuration adaptée pour utiliser ces kind of d'empilement.
Normalement, la grande partie de l'anisotropie, ça vient de la structure du matériau lui-même, la structure cristalline.
Mais ici, en jeu, on concentre sur ou bien les hypothèses de base, c'est que l'époxy est un matériau isotrope et les fibres ce sont aussi des matériaux isotropes. On fait le mélange. On utilise la loi de mélange pour déterminer les paramètres de chaque plique. Et ensuite, on joue sur l'angle d'orientation pour trouver la meilleure configuration.
Si vous permettez, le monsieur parle des propriétés matérielles. C'est l'anisotropie, orthotropie et isotropie. Donc on doit descendre un petit peu à l'échelle
micro.
Afin de voir cette propriété intersecte qui est liée au matériau. Donc si on se met dans le cas aniso, et on a des plans de symétrie à l'échelle cristallaire, là on va sauter vers le plan, vers la propriété orthotrope. Donc c'est un peu ça. Maintenant, si le monsieur parle plus quelle est l'énergie qui a induit cette anisotropie. Moi, à mon avis, c'est lors de la fabrication, c'est elle qui va influer à l'échelle cristalline, qui va engendrer cette différence de properties. À mon avis.
Donc, je vous remercie.
Merci, monsieur.
Et bonne continuation.
Maintenant, c'est
de